I welcome you all for the Maxwell's thermodynamic relations. Generally, the students in the second semester or third semesters feel very difficult with this thermodynamic relation. The property of any fluid, namely the gas, or pressure, volume, and the temperature. The Maxwell thermodynamic relation includes one more property, namely the entropy, S. And if I can formulate these properties, pressure, volume, and temperature, and entropy, in terms of PDE, partial differential equations, they results in the formation of Maxwell's thermodynamic relation. So before going directly to the Maxwell thermodynamic relation, let us establish what do you mean by cyclic relation. So let us discuss about the cyclic relation. Let us consider a function f which depends upon the variables x, y, z, and let us take a function f of x, y, z equal to 0, and let x be defined as x of y comma z, and y is defined as y of x comma z, and z is defined as z of x comma y. So we have taken a function f of x comma y comma z equal to 0 with these things defined. Now x depends upon y as well as z. So we have to differentiate partially if I want to have the differential of x. So let me write what is meant by dx. So dx is nothing but dou x by dou y into dy plus dou x by dou z into dz. That is, here x depends upon two variables y and z, and since we want to study about both these variables, we are going to differentiate partially with respect to y, keeping z as constant, and we are also going to differentiate x partially with respect to z, keeping y as constant, where dx is the exact differential. Let us name this equation as equation number 1. Similarly, let us try to write the exact differential for y and z. So dy will be equal to dou y by dou x into dx plus dou y by dou z into dz. When I am going to differentiate y with respect to x, I have to maintain z as constant. Similarly, when I am going to differentiate y with respect to z, I want to maintain x as constant. Let us name this equation as 2, which gives the exact differential of y dy. Similarly, we can write for dz also. Dz equal to dou z by dou x into dx plus dou z by dou y into dy. So when I am going to differentiate x, y should remain constant. Similarly, when I am going to differentiate z with respect to y, x should remain constant. Let us name this equation as 3. Let us name this equation as 3. So I hope you can understand how we derive dx, dy, and dz. Let the equation number 1 can be represented as dx equal to m of dy plus n of dz, where m is equal to dou x by dou y. Similarly, n is equal to dou x by dou z at constant y. Let us now try to obtain the second order partial derivative. Let us have dou m by dou z. So differentiate m with respect to z now. So the resultant will be dou squared x by dou y dou z. Let us call this equation number as 4. And similarly, let us differentiate n with respect to y. So we will get the second order derivative. So it is dou n by dou y is equal to dou squared x by dou y dou z. Let us call this equation as equation number 5. From 4 and 5, we can see that the right hand sides are equal, dou squared x by dou y dou z, which means dou m by dou z will be equal to dou n by dou z equal to dou n by dou y. These concepts we will be using in near future to derive the thermodynamic relationship. That is, when you are going for the second order derivative, dou m by dou z and dou n by dou y remains same. Now let us take the equation number 2 and 3. We can see here dy is given by dou m by dou x at constant z into dx plus dou y by dou z at constant x into dz. Once again we have another equation for dz. Now substitute the value of dz from equation number 3 in equation number 2 at the place of dz. Okay, so let us write dy equal to dou y by dou x at a constant z into dx plus dou y by dou z at a constant x. Now for this dz, I can substitute from equation number 3. So it is dou z by dou x of y into dx plus dou z by dou y of x into dy. Yes. Let us call this equation as equation number 6. Third expression. Now just I am going to do some mathematical simplification. So there is no change in the first term, dou y by dou x of z dx. So multiply this term with this one, as well as this term with the second term. So it is dou y by dou z at x into dou z by dou x at y dx plus dou y by dou z at dx into dou z by dou y at x into dy. So we can see from the first two terms dx is a common term. So we can take dx as common term between the first two terms, dou y by dou x. It can also be written like this. Either we can write with a vertical bar and z, or we can put a bracket with suffix z, both are same, plus dou y by dou z at x into dou z by dou x at y. So I am taking dx common within these two terms. Here it will become dou y by dou z at x. Similarly, dou y by dou z by dou y at x into dy. The left hand side is still dy. What will be the value of this term? The value of this term will become 1 because dou y get cancelled, dou z cancel because both are having the same suffix as x. So this term will become 1 into dy. So the resultant value will be dy over alone. So we can see dy equal to dou y by dou x of z plus dou y by dou z of x into dou z by dou x of y of dx plus this term will go away, it become 1 into dy or simply dy because the value of this term is 1. So what happens, you can see here. Here also dy, here also dy. If you are going to take this dy to this side, dy minus dy will become 0. So it becomes 0. 0 equal to the same term will come. So dou y by dou x of z plus dou y by dou z of x into dou z by dou x of y of dx. Now the product of these two terms is equal to 0, but we know that dx is an exact differential or is an operator which cannot be 0. Dx cannot be equal to 0, which implies the other term within this square bracket should be equal to 0. Because dx is an exact differential and it can't be 0, so the term within this bracket will be equal to 0. So it is dou y by dou x of z plus dou y by dou z of x into dou z by dou x of y is equal to 0. The next step is I can take another term to the other side. So it will become just mathematical work, dou y by dou x z of x into dou z by dou x of y is equal to minus dou y by dou x of dz. Let us simplify further. So this is the term we got. Now we can even bring this term to the other side by cross multiplying it. So when I am going to cross multiply, it will become dou x by dou y of z, because it will become, when I am going to do the cross multiplication, it will become dou x by dou y of z, then dou y by dou z of x into dou z by dou x of y. What is the right hand side? The right hand side is minus 1, because this term is taken, so we are getting minus 1. Always multiply the entire left hand side and right hand side by dou x by dou y, we will end up with minus 1. So this relation is called the cyclic relation. This relation is generally termed as called as what? Cyclic relation, which is very important for deriving the Maxwell relation. Cyclic relation. Generally, the property of any gaseous fluid mainly depends on pressure, volume, temperature, and in Maxwell relation we are going to include entropy also. So we are going to study about these four parameters or four properties: pressure, volume, temperature, and entropy. So this volume is nothing but specific volume. This T is temperature, this S is entropy, all are specific quantity, and hence we will proceed further. The importance of this equation is that we can see here dou x by dou y. It will start with dou y and ends with dou z. Once again start with dou z and ends with dou x. This dou x will be coming here. So it forms a cycle 1 and hence is called as a cyclic relationship. If you have x and y, the other variable will come z. If y and z is there, the other variable is x. If z and x is there, the other variable is y. So we will end up with dou x by dou y of z into dou y by dou z of x into dou z by dou x of y equal to minus 1. Here, you can take x, y, z as any variables. For example, let x equal to t, y equal to p, and z equal to s, or even you can take y equal to v, nothing wrong. Anything you can take. So x, y, z indicates here the variables rather than the simply mathematically saying x, y, z. Let us go with the thermodynamic properties. So the same relation can be written as dou t by dou v into dou v by dou s into dou s by dou t equal to minus 1. Here T and V is there, so the remaining variable is S. Here V and S is there, so the remaining variable is T. Here S and T is there, so the remaining variable is V. So I hope now we can appreciate the use of the cyclic relation. So we have the T, V and SF or XI is there, and we establish the cyclic relation based on this equation. Similarly, you can take X equal to S, Y equal to P, and Z equal to V. Anything. There's no need you have to take only SPV or PVS. Anything you can use. Now the relationship will become dou S by dou P and dou P by dou V. The third variable is V. Then dou V by dou S. We have to come and complete with S. Then only it becomes cycle equal to -1. So here we have variables as SPV. So we have SP. So the remaining will be V. Here P and V is there. So the remaining will be S. Here V and S is there. So the remaining will be P. So like this we can formulate any number of cyclic relationship for the thermodynamic properties what we are going to investigate. Let us move further and discuss and establish the Maxwell relation. So far we have seen what is meant by cyclic relationship and how it has been derived. And there is one more rule called as chain rule. So far what we have seen is called as cyclic relation, and one more rule is called as chain rule. For example, chain rule deals like this, that is dou T by dou V into dou V by dou T. Let's take the third, not a second variable, let us take the third variable as S and dou S by dou T. Now this value will be equal to 1. Not -1 plus 1, only when all are going to have the same function, say P or V or T. Okay, now the value will be equal to 1. Why means dou T will get cancelled, dou S will get cancelled, dou V will get cancelled. So the answer will be equal to 1. Or instead of P, it can be another parameter, say V also. And all are taking place as constant volume. Now also the value will be equal to 1. So this is nothing but the chain rule. The chain rule says a chain has been formed. It's starting at T, ending at V. The end should be the starting for the next one. So dou V by dou F. S is the ending, the starting should be dou S. Ending is dou T, the starting is dou T. So, but it should take place at constant property. Either it can be volume or pressure or temperature. Then only the value will be equal to 1. So these two things you should have to remember for deriving the Maxwell relation. Okay. Let us now come to the exact Maxwell relation derivation. Let we know the first law of thermodynamics applied to a closed system, Q equal to W plus delta U. If I am going to differentiate, then it will become dQ equal to PdV plus du. And we know the area under the TS diagram is nothing but the heat transfer dQ. So the dQ can be replaced with TdS. Also we know that the area under the PV curve is nothing but the powder. So it is PdV plus du. Now from this I want du only. So du equal to TdS minus PdV. So let us name this equation as this first law of thermodynamics is 5, this equation is 6. Now based on this expression, we can see U is a function of S and V. So we can say that U is varying with respect to ds and dv, and hence U is a function of S and V. Since there are two variables, I can maintain one as constant and study the effect of the other one by varying it. So let us say first for constant entropy. Constant entropy is always called as isentropic. For a constant entropy process, that is S equal to 0, S equal to C, which means ds equal to 0. I am going to apply this particular rule over here. Then what will happen? This ds will go away. then it will become dou u by dou v at constant entropy. So this term is 0. So dou u by dou v at constant entropy will be equal to minus p. I hope you can understand. So I will repeat once again. I have d equal to TdS minus PdV. Now we can see that u is a function of both entropy and specific volume V. In order to study the effect of both the things, first I have to maintain one is constant. So first thing I maintain the entropy as constant. So which means ds will become 0. So this will become dou u by dou v equal to minus p at constant entropy. Okay. Now as I told earlier, we can go for the second derivative. We can go for the second derivative. Now differentiate this one with respect to s, with respect to entropy. So dou squared u by dou v dou s will become minus dou p by dou s at constant volume. So now we have to maintain volume as constant, and I am going to differentiate this equation. So it will become dou squared u by dou v by dou s. Dou v into dou s will be equal to minus dou p by dou s at v. So let us make this as equation number 7. This is the second derivative, and obtained by differentiating with respect to the entropy by maintaining the volume as constant. Now let us take the other way. The other way is, instead of keeping entropy as constant, let us take volume as constant for isochoric process. For isochoric process. Isochoric means volume remains constant, which means dV equal to 0. So this term will become 0 now. So what will end up with? We will end up with dou u by dou s at a constant volume equal to t. Dou u by dou s at a constant volume will be equal to t. The next step is to differentiate once again this derivative with respect to volume. So I will end up with dou squared u by dou s dou v equal to dou t by dou v at constant entropy. At constant entropy. You make this as equation number 8. You make this as equation number 8. From 7 and 8, you can see that the left hand sides are equal. Dou squared u by dou v dou s. Dou squared u dou v dou s will be equal to dou squared u by dou s dou v, because both are saved. So the right hand side should also be equal. So I can write from 7 and 8, we can tell that dou t by dou v at constant entropy will be equal to minus dou p by dou s at constant specific volume or volume. So this one is called as Maxwell first relation of thermodynamic, or Maxwell first thermodynamic relation. So dou t by dou v at constant entropy will be equal to minus dou p by dou s at a constant volume. I hope you can understand. Let us move to the second one. This we derived based on the first law of thermodynamics, Q equal to W plus delta U, by substituting for du, Q and W. Now let us proceed with the same one. For applying the second relationship, okay, in here we will start once again with the first law of thermodynamics, Q equal to W plus delta U, which means dQ equal to dW plus du. So TdS equal to PdV plus du. Also we know that the enthalpy, specific enthalpy HE is given by U plus PV. So dH will be equal to du plus d of PV, which will be du plus PdV plus VdP. This is but dH. From this, what is du? From this the du will be equal to dH minus PdV minus VdP. So let us have some equation number. Say it is 9. This is 10. Substitute 10 in 9. So once again I use the first law of thermodynamics only. We end up the same equation Tds equal to PdV plus du. But I want to substitute du in terms of enthalpy. So I already know that H equal to U plus PV. From that du will be equal to dH minus PdV minus VdP. Okay, fine. Now substitute here. Tds equal to PdV plus dH minus PdV minus VdP. So what will happen? This PdV and minus PdV will go away. So the final expression what I obtained will be Tds is equal to dH minus VdP. Tds equal to dH minus VdP. From this I will get the value of dH. dH equal to Tds plus VdP. In the last derivation we ended with du. In this expression we are ending up with dH. That is enthalpy. In the Maxwell first relationship we ended up with du. Here H is a function of what? Here H is a function of S and P. Because ds is there, dp is there, so H is a function of S and P. Now as usual, we have to keep one variable as constant and differentiate with respect to other and find a second derivative. Similarly, we have to proceed and try to establish the second Maxwell relationship. I hope I can go a little fast. So first, as usual, for isentropic process, which means S equal to constant, otherwise ds equal to 0. I am going to apply it for here. So dou H by dou P, because this term will become 0. So dou H by dou P at constant entropy will be equal to V. So we are going to find the second derivative. The second derivative will be equal to dou square H divided by dou S dou P. Now differentiate with respect to S will be equal to dou V by dou S at constant pressure by maintaining the pressure as constant. Let us call this is equation number 12. So this is being derived by assuming or by taking the entropy as constant and we find the effect of H on P. Now we are going to do the other way for isobaric process. For isobaric process. Isobaric means P equal to constant or dP equal to 0. So dP equal to 0 means this term will become 0. So which implies the equation 11 will become dou H by dou S at constant pressure will become T. Differentiating once again to get the second order derivative. So this dou squared H by dou S dou P will be equal to dou T by dou P at the constant entropy. So let us say this is equation number 12. Sorry, it's 13. From these two expressions we can see the left hand sides are equal, which means the right hand side should be equal. Which says that dou V by dou S at a constant pressure should be equal to dou T by dou P at a constant entropy. One more thing is, we can see here dou S means P will come. Here it will be the other way, dou P at S. Here also you can see dou V at a constant entropy. So it should be the other way. So dou S at a constant volume. So this is nothing but called as, this expression is called as Maxwell second relation or second thermodynamic relation. It's very simple to derive. Maybe I am taking more time to derive. But once if you understand, we can derive within 5 minutes. Now let us proceed further to derive the Maxwell's third relation and fourth relation. So this is first one, this is second. For deriving the third relationship, I am going to use the function Helmholtz function A equal to U minus Ts. The first Maxwell relation is based on du. The second Maxwell relationship is based on dh. Similarly, the third Maxwell relation, what we will be getting here, is based on dA. dA or A is nothing but the Helmholtz function given by U minus T into S. Now, dA will be equal to du minus d of Ts. So, it will become du minus T into ds minus S into dt. Once again, we can substitute the value of du here. So what is du? Q equal to W plus delta U. So dk equal to dW plus du. TdS equal to PdV plus du. So from this, du is nothing but TdS minus PdV. So substitute for du in this expression. So it is TdS minus PdV minus TdS minus SDT. I hope you can easily understand this concept. Just I want to substitute the value of du from the first law of thermodynamics. I have substituted the value of du as TdS minus PdV from this expression. Now which term will cancel? The TdS and minus TdS will cancel away. So the dA is nothing but minus PdV minus S into dt. Now, what is A? A is a function of? A is a function of V and T, because dV is there, dt is there. So, A is a function of V and T. Once again, I am going to repeat the same step. I will be little fast. I want to derive by keeping temperature as constant and differential with respect to volumes partially, and I will get the second order derivative. Similarly, the other way, I will keep volume as a constant, differential with respect to temperature, and find the second derivative. Okay. Now, for constant volume or isobaric, so V equal to C, which means dV equal to 0. So this term will become 0. So dou A by dou T equal to minus S at a constant volume. At a constant volume. Now differentiate once again. It will become dou square dA by dou T dou V equal to minus dou S by dou V at a constant temperature. So this is the expression we obtained by maintaining volume as constant. Now we can go for the other way. Now for isothermal process, which means T equal to constant or dt equal to 0, which means this term will become 0 now. So dou A by dou V at a constant temperature equal to minus P. So do once again the second order derivative, differentiate once again. So dou square A by dou V into dou T will be equal to minus dou P by dou T at constant volume. At a constant volume. As usual, you keep this as equation number 14, this is 15. We can see that the left hand sides are equal, so the right hand side should be equal, which indicates that minus dou P by dou T at a constant volume will be equal to minus dou S by dou V at a constant temperature. So this minus multiply both sides by minus sign, so become positive. As usual, dou T and V is taken outside. So the relationship should be dou V and T. So this relationship is nothing but called as our Maxwell's third relationship. Let us write it here. So it is dou S by dou V at constant temperature is equal to dou P by dou T at a constant volume. So this is called the Maxwell's third relationship, which is obtained from the Helmholtz function. The first Maxwell relation is obtained from the internal energy. The second Maxwell function is obtained by the enthalpy. The third one is obtained from the Helmholtz function A. Let us deal with the last one. The last one is based on Gibbs free energy function. So G is nothing but Gibbs free energy, which is given by H minus Ts. So if I am going to derive the relation with respect to dG or G, it is nothing but called as my Maxwell's fourth relation. So G equal to H minus Ts. I will make it fast because I hope you can understand. dG equal to dH minus d into of Ts. So dH minus T into ds minus S into dt. So what is dH? H equal to U plus PV. So dH is equal to du plus PdV plus VdP. What is du? Just now we derived. Once again we make it fast. So Q equal to W plus delta U. So dK equal to dW plus du, or TdS equal to PdV plus du, or du equal to TdS minus PdV. So substitute for du here. So it become TdS minus PdV plus PdV plus VdP. So from these two terms, plus PdV and minus PdV will get cancelled. So dH will be equal to TdS plus VdP. So substitute once again this dH over here. So substitute here. So it is T into ds plus VdP minus TdS already existing there minus S into dt. So ultimately our aim is to, there should be only one variable, either internal energy or enthalpy or Helmholtz function or Gibbs free energy function. So there should not be both G and H. So I have replaced G with the normal variables. So the resultant function will be dG equal to this term and this term will get cancelled, VdP minus S dt. Now we can see G is a function of what? This is a function of P and T. So G is a function of P and T. As usual, first we can maintain pressure constant, division with respect to T, get some second order derivative. Then make T as constant, division with respect to P, second order derivative. Compare them, you will get the fourth Maxwell relationship. Let us make it fast. So for isobaric process, P equal to C, otherwise dP equal to 0. So this first term will go away. So it becomes dou G by dou T at a constant pressure equal to minus S. Differentiate once again the second order to get the second order. So dou square G by dou T dou P at dou T dou P will be equal to minus dou S by dou P at a constant temperature. Okay. If you want, we can give the equation number 16 or some numbers. Okay. Now we will take the other part for isothermal process. For isothermal process, that is T equal to C, otherwise dt equal to 0. For T equal to C or dt equals 0. So this term will become 0 now. So it will become dou G by dou P at constant temperature equal to volume. Differentiate once again. Dou square G by dou P dou T will be equal to dou V by dou T at a constant pressure. At a constant pressure. It is nothing but something. As usual, the left side will be equal dou square G by dou P dou T. Here is dou square G by dou P dou T. So the right hand side should be equal. So that ends up with our fourth Maxwell's relation. So the fourth Maxwell relation will be like this. Dou V by dou T of P will be equal to minus dou S by dou P of T. So this is nothing but the Maxwell's fourth thermodynamic relation based on the Gibbs free energy. This is Helmholtz function. This is based on enthalpy and this is based on interenergy. And my professor, my colleague Professor T. Srinivas used to explain us, whenever you sit before TV, it's not good, it's negative. So we have a negative sign here. So a minus sign ends up here. And in the last expression also we have TV. So there's a negative sign. So whenever you are going to sit before TV, it's just for recalling the idea. There's nothing with the thermodynamics. But whenever we have TV, definitely we will end up with negative sign. Here also we have VT or TV, so there will be negative sign. So just to recall the relationship. In the next session, we will discuss how to obtain this Maxwell relationship or the second Maxwell, third relation, fourth relationship from the first relation itself by using the cyclic relation and the chain rule. Thank you. Yeah, in continuation of the last session, we derived the Maxwell first, second, third, and fourth relationships from the fundamental basics law, namely the enthalpy, entropy, Helmholtz function, and Gibbs free energy. We can also derive the same relation, second, third, and fourth thermodynamic relation from the first thermodynamic relationship. That is what we are going to discuss for the next half an hour. So we are going to derive the Maxwell second, third, and fourth relationship from the first Maxwell relation by utilizing the cyclic relationship and the chain rule. Okay. Let us now proceed with the cyclic relationship. The cyclic relationship says that dou x by dou y into dou y by dou z into dou z by dou x equal to minus 1. So you can see there is a cycle. It's end up with y, starts with y. It's end up with z, start with z. It's end up with x, start with x. So it will be a cycle 1. As I told you earlier, if there is x and y, the third variable should be outside. Y and z means that last variable is x. If z and x means it is y. Okay. In order to derive the Maxwell second relationship, we have to use x equal to t, y equal to v, and z equal to s. Simply to recall, we can keep it as TVS. TVS may be utilized for getting the second relationship from first one. So now let us implement in this cyclic relationship. So it will become dou t by dou v into dou v by dou s into dou s by dou t. It should start at dou t, it should end at dou t. So t and v is there means s should come. V and s is there means t should come. S and t means there should be v should come equal to minus 1. Is equal to minus 1. Just I am applying the cyclic relationship by making use of x, y, z as t, v and s. Now I am going to make the second term alone to take it to the other side. So it will become minus dou s by dou v, yeah, at constant temperature will be equal to dou t by dou v at a constant entropy and dou V by dou S at constant temperature. Sorry, this term already we have taken to the other side, because this term already we have taken to the other side. So the remaining term will be this one only. So it is dou S by dou T at a constant volume. So the first rule is we are applying the cyclic relationship by using X, Y, Z as TV and S. The second point is that we have to make use of the first thermodynamic law. So what is dou T by dou V at constant entropy? It is nothing but minus dou P by dou S at a constant volume. So replace this first term with the corresponding term in the Maxwell first relation, because we are going to derive all the relationship only from making use of the first relationship. So I can substitute for dou T by dou V at constant entropy with this one. So it is minus dou P by dou S at constant volume into dou S by dou T into constant volume equal to minus dou S by dou V at constant temperature. Now multiply both sides by minus sign, the minus sign will go away. So we are ending up with dou P by dou S at constant volume into dou S by dou T at constant volume is equal to plus dou S by dou V at a constant temperature. Now we have to make use of the chain rule. The condition for deriving the other three relationship are like this. The first one is to use to the cyclic relationship. The second one is to we have to substitute some values from this Maxwell first relationship, and the third concept is to apply the chain rule. So what is chain rule? The chain rule says that dou X by dou Y into dou Y by dou Z into dou Z by dou X will be equal to 1. When it will be equal to 1? When all the variables are going to be some constant variable, say X or say Y or say Z. Here the common variable is what? V. But there are only two terms, but there should be three terms in the expression. I will come up with that one. So it is dou P by dou S. The first two variables are P and S. The second variable is S. The third variable is T. So you should start with what? Dou T and end with what? Dou P. I hope you can understand, because there are three variables P, S and T. If you want to write as a chain rule, so dou P by dou S into dou S by dou T into dou T by dou P will be equal to 1. When will be equal to 1? When all are equal to, when all are taking a constant volume, then only it will become 1. Okay. Now, from this chain rule, what we want only up to here. From this chain rule is common one. From this chain rule we can see what is the value of the first two terms, because we have already this first two terms. So this value will be equal to dou P by dou S at a constant volume into dou S by dou T at constant volume will be equal to dou P by dou T at a constant volume. So it can be taken here, dou T will come here, whereas the volume will be remain same. So the left hand side all this equation can be replaced by dou P by dou T at a constant volume. So I am going to replace this one. So it is nothing but dou P by dou T at constant volume. As I told you earlier, dou T at P means it should be dou V at T. So we can see whether this is there or not. Yeah, we can see here dou S by dou V at T. So here we are ending up with it's not the second relation actually. Yeah, it's really right. It is Maxwell's third relation. We will end up with the Maxwell's third relation. So dou S by dou V at T is equal to dou P by dou T at V. So this relationship is what we derive is not Maxwell's second relation, is the Maxwell's third relation. That's nice. Similarly, we have to apply the concepts to obtain the second relationship and the fourth relationship. Okay, so let's proceed further and we will try to complete little faster. So what are the three steps we follow The first step is cyclic relation. The cyclic relation is obtained for TVS. Then we substitute some term from Maxwell's first relation. Then the third step is we made use of chain rule. When we completed the three steps, we ended up with the Maxwell's third relation. Now I am going to do the same thing. I am going to follow the three steps for deriving the second relation as well as the fourth relation. Let us proceed further now. Now x equal to s, y equal to p, and z equal to v, SPV. Here we can, similar to earlier we taken as TVS. Now we can take as SPV, and we will write the cyclic relation. So I will make it fast. So it is dou s by dou p at a constant volume into dou p by dou v at constant entropy into dou v by dou s at constant pressure will be equal to -1. Now these variables are varying, means here I will end up with -1. If these variables are same, I will end up with +1. That is the only difference between the cyclic relation and the chain rule. Okay, so dou s by dou p at constant volume, dou p by dou v at constant entropy, like this. Now I will maintain this dou v by dou s alone here. So dou v by dou s at constant pressure will be equal to, if I am going to take that side, it becomes dou p by dou s at a constant volume. Already minus sign is there. Then dou v by dou p at constant entropy. So what I did, among the three terms, I retained dou v by dou s at constant pressure on the left hand side, whereas I taken the other two terms to the right hand side. What is the second step? The first step is applying the cyclic relation. What is the second step? To substitute for the Maxwell relation. So which term I can replace? Minus dou p by dou s at constant volume. Here also I am having dou p by dou s at the constant volume. So replace this term with dou t by dou v. So I can replace this term with dou t by dou v at the constant entropy. Now what the third rule says? Apply the chain rule. How we can apply the chain rule? Because both the variables are same. So I should get what the third term. So first of all we will write the chain rule. So it will become dou t by dou v and s into dou v by dou p and s. What will be the third term? It will be dou p by dou t at constant entropy will be equal to 1. Because all are s, so the value will be equal to 1. Now from this one, what is the value of dou t by dou v of s and dou v by dou p of s? So from this one I want this value. So this will be equal to, or I will write once again, dou t by dou v of s into dou v by dou p of s will be equal to dou t by dou p of s. So this term, the right hand side term, can be replaced with what? Dou t by dou p at s. So this is nothing but dou t by dou p of s. So that's it. Because we have applied all the three tools we have. We have applied the cyclic relation, we have applied the Maxwell relation, first relation, and we have applied the chain rule also. So we can see here dou v by dou s at p, dou v by dou s at p equal to dou t by dou p as p is s. So this is nothing but we derived the Maxwell's second relation. So by taking TVS, we ended with the third relationship. By taking SPV, we ended with the Maxwell's second relation. So let us move to the last one. There is nothing but the fourth relationship. In the fourth relationship, there is no need to apply the chain rule, but it's slightly varying. I will deal with you. The first two concepts remain same. Here we will put as VTP. So So x equal to v, y equal to t, and z equal to p. First one starts with the TVS, second one starts with the SPV, the third one starts with the VTP. So let us proceed further. So I will first just to obtain a cyclic relationship based on V, T and P. So dou V by dou T at a constant pressure into dou T by dou P at a constant volume into dou P by dou V at a constant temperature is equal to -1. Is equal to -1. Once we get the cyclic relationship for V, T and P like this one, let us retain dou V by dou Tp along in the left hand side and take the other variables to the other side. So it is dou V by dou T at a constant pressure is equal to dou P by dou T at a constant volume into this dou V will go to the numerator, so it is dou V by dou P at a constant temperature. But now there is no term. The second step is what? We want to substitute some values from the Maxwell first relationship. There is no dou T by dou V at constant entropy term, so I can't replace the left hand side term. So in the right hand terms also I don't have dou P by dou S. So here only we have to make a small assumption, or we have to make a small work, that is multiply and divide by dou S. The value will not get changed into dou S by dou T of V. Now we can see dou S and dou S will get cancelled, so the answer will not vary. Why we made like this? Then only I can replace this dou P by dou V. Here also I forgot to put a minus sign because the minus one is there. Here also the minus sign will come. So it is minus dou P by dou S into V. This term can be replaced with dou T by dou V of S into dou S by dou T of V. The third term, for this term also, you multiply and divide by S. So it is dou V by dou S at T into dou S by dou P at T. This minus is, yeah. So the second step after writing the cyclic relation, the second step is to substitute the value from the Maxwell's first relation. So this value will become dou T by dou V at S into, now I am writing the third term as my second term, there is nothing wrong. So dou V by dou S at a constant T. I am writing the second term as the third term, dou S by dou T into V at a constant volume into dou S by dou P at T. What is the left hand side? It is dou V by dou T at P. Can anyone tell what is the value of this one? Dou T by dou V, then followed by dou V by dou S, followed by dou S by dou T. Whether it is following a cyclic relation or a chain rule. It is following cyclic relation or chain rule. Here the variables are same or different? The variables are different. So it is following a cyclic relation. So what is the value of these three terms? -1. This value will be equal to -1. So now it's time we can erase these two things. So it will become dou V by dou T at P will be equal to minus dou S by dou P at T. Now we can check whether this is same or not. Yeah, dou V by dou T at P, dou V by dou T at P equal to minus dou S by dou P at T. So we have derived the Maxwell's second, third and fourth relationship from the first relation by making use of the cyclic relation and substituting the value from the Maxwell first relation and making use of the chain rule. For deriving the last equation, there is no need of the chain rule, just we want to apply the cyclic relation. Yeah, thus we saw we can derive the Maxwell's relation, the four relationships, either from the basic formula of enthalpy, energy, Helmholtz function and Gibbs free energy function. Otherwise, we can derive from the Maxwell's relation by pure mathematics. I hope definitely this will give you some basic understanding of the Maxwell relations. I wish to thank my research scholars John Samuel, Arun Sacco, and Dinesh for their ultimate help in making this video lecture a more positive one. Thanks, sir.